Okay, I promised you all that I would finish up these last three problems in chapter 17 with video. So here we go. Looking at part B, we know that the beat frequency is always equal to the difference in the two frequencies being played together out loud. And it's the absolute value between the two. So if you have 352 hertz for one tone and 297 for the other tone, you get 55. And so that's the pulsing sound that you hear coming from playing two notes together. And I got those frequencies right here because it was the notes D and F. On this one, part A, we didn't finish this one up, but when the objects are approaching each other, it's all about adjusting these numbers right in here. Now, because of the zero, the top doesn't really matter, but what you do is if these two objects are approaching each other, you use the top number. So another, I'm sorry, not the top number, but the top sign. So that would be this right here and that right there. And so for part A, when they're approaching each other, let me make sure that they are oncoming, right? And so for this one, the frequency that you get ends up being for the subtracting those two together. So it's going to be greater than 800. And then over B here for part B, we're going to take, let's do the green for this one. These objects are moving away from each other because you can see that right here, it says after it passes. Excuse me. So I'll try to use green for that one. And that's the observed frequency is equal to the source frequency and then times those ratios. Let me pause the video and I'll do those calculations. All right, so then doing those calculations in the calculator, you get a higher pitch coming towards you, 878 hertz. So that's the wee sound as it goes approaching you. And the oo sound of something going away from you with the lower pitch sound is 735 hertz. On this last one, it's dealing with shock waves. If an airplane is flying at Mach 1, let's see if we can represent that airplane going with a velocity here. So a known would be that's Mach 1.50. And it looks like this right here is the speed of sound. So all that really means is 1.50 times 343.00 meters per second. And so doing that in a calculator over on my other screen, I'm going to get 1.5 times 343, and I'm going to get a speed of 514.50 meters per second. So they're going faster than the speed of sound in this case by 50%. The altitude that they're going to be at for our sketch over here so they're going like that. And the distance above the ground right here is going to be, let's see, I think they put it right here on paper, 7500.00 meters. Now, if you look at figure 17.36 in the book, you'll see that behind the aircraft, excuse me, there is a cone shape. And if you do a dotted line through the middle of this right here, this angle theta is related to, oh yeah, what is our unknown? So our unknown is going to be, okay, how far away they are. We'll put this as R, that'll be the value. And so the solution will be basically to figure out what this distance r is, because we want to put the little person right down here where they hear the sonic boom. So they are going to be hit by this pressure wave, and that's when they hear the boom. And so this r is the distance from you to the aircraft when that happens at the moment. And then so you can see that there's this sine theta, I believe. So sine theta would be equal to this height h over r. So if you're looking for r, then it's going to be h divided by sine theta. But in figure 17.36, and also in the equation on the same page that follows, there's another connection between the sine of theta and physical parameters. And that is, if you take the speed of sound over the speed of the source of that sound, or basically 1 over the Mach number. Now, let me make sure I got that right, because sometimes they use v sub s for something else. So the Mach number is, yeah, this is the speed of the aircraft right here, and that's the speed of sound. They're kind of making it easy for us then, because then it's just 1 over 1.5, like that. Then you do that in a calculator, get something kind of easy, right? 1 over 15. And you get 6 repeating. Okay, so that is the value of the sine. I'm just double checking to make sure I did everything properly. Okay, and so then if you plug that back into the value of r, you have h over the sine of theta equals the 7,500 kilometers over 0.6 repeating. This is going to tell you what that radial distance is in the diagram. So then I'm just going to take that approximation as 7,500 divided by 0.6 repeating, and I get that it's 11250 kilometers away. Okay, so you had to kind of go within the chapter to figure out that there's this angle of the shock wave, and the faster you go, the narrower that point on the end of that shock wave. All right, I believe that's all in this chapter. I'll make another video for the next chapter if we need to. All right, I'll see you in class.